So I'm going to be going into more detail about some of the things I outlined yesterday. Can I ask how many people did hear what my talk yesterday? I want to get an idea of how many have already. Okay. So on some of these things, I'll be repeating some of the slides, and I'll go a little quickly because you've already seen some, and then I'll slow down when we get to the newer ones. But it helps to have everything there to give it the context. My collaborators specifically on the thermodynamics work have been Tom Greenbow from the chemistry department at Iowa State, and he and I started work on this very early on, about 7 years ago, where we're doing a combined project, excuse me, looking at student learning of thermodynamics in both the physics and the chemistry department. And more recently, John Thompson at the University of Maine in the physics department. Several students contributed to this, including Naklan Win, Warren Christensen, my current PhD student, and Tom Stroman. And we've gotten funding from the U.S. National Science Foundation, from the Division of Undergraduate Education, and also from the Division of Physics. The basic aim of this project is to investigate student learning of statistical thermodynamics, but tracing students, the development of students' learning, the development of student thinking from their first exposure to thermal physics in the introductory university course up through their advanced level undergraduate course. And it's probably worth remembering that the introductory level university course at American universities is probably approximately equivalent to your final year of upper secondary school in most cases, as I understand it. It is, although they have, the students in these courses have already had 1 year, generally 1 year of study in their secondary school as well, but only 1 year. Based on the research, we developed curriculum materials and instructional methods. And as I say, most recently, this is in collaboration with a group at Maine. There have been studies on, now focusing on US universities, there's been studies on student learning in the algebra-based introductory course. This would be the course that's taken by non-physics majors, by, say, biology majors or pre-medical students. That's the algebra-based introductory course. And there has also been some studies at an upper level, a second-year course at the University of Washington. And in the calculus-based introductory course, that is the course taken by engineers. And I'll be discussing some of the results from these studies as well, but my focus will be mostly on the upper level course, the course taken by physics majors in their third or fourth university year, where they generally study statistical mechanics, but I will not be discussing today the learning of statistical mechanics. It'll be mostly macroscopic topics, macroscopic thermodynamics. The general results from the introductory courses, and I will go into some of the data in more detail, is that students leave their first-year university course, not just in American universities, but in many other countries as well, with very weak understanding of some of the key concepts, including the first and second laws of thermodynamics, basic ideas like heat and work, entropy, and so on. And as I mentioned yesterday, there have been studies on students in the United States, in Germany, France, and the United Kingdom. Well, I will say that the studies in other countries have been very limited. This is pretty much all that you can find, that I've been able to find in the literature on students at the university level in thermal physics. And these studies in the United States have all been pretty recent. Now, this started out as a focus on the students in the second semester of the first year calculus-based introductory physics course at Iowa State University, where most of the population are engineering students. It's required that they take that course. We gave a series of written questions, short set of written questions that were administered to about 650 students over a 3-year period in that course. And then in the fourth year, we got volunteers from the course to come in and do one-on-one interviews. And in these interviews, we sit down, the investigator and the student, one-on-one, and we talk to them for about an hour or more. We audio tape or videotape the interviews, and they describe their reasoning as they go through a series of problems. Now, all of these tests and all of the interviews were carried out after instruction on thermodynamics was completed for these courses. And what I want to emphasize, as I mentioned yesterday, is that the students who volunteered to be interviewed were above average in their performance in their course grades. And I wanted to show, well, I'll show the graphic again in a moment. Just to summarize the findings, and again I'm going to show the details in a moment, after instruction in these introductory courses, between 40 and 80% of the students believed or acted as if they believed that both heat and work are state functions independent of the process, and believe that in a cyclic process, the net heat transfer to a system, the net work done by a system have to be equal to zero. And in general, they're nearly not able to make effective use of the first law of thermodynamics in solving problems. The majority of students in these classes, that's what the data will show. Now, speaking about the advanced course, the upper level course, this would be typically taken in their third or fourth year. It is their last year of university or the year before their last. In this course, the way I teach it, it's a roughly equal balance between topics in macroscopic thermodynamics and topics in statistical thermodynamics. The text that we used when I taught the course were Sears and Salinger and the book by Schroeder on thermal physics. Relatively small enrollments, 14 students in 2003 and 19 students in 2004. And as I understand it, your enrollment in these courses here is significantly larger than that. But that is a pretty typical number, even for a large state university. Iowa State University is one of only 2 state universities in the state of Iowa. And the population in Iowa is not that far from the population of your entire country. And nonetheless, in this class, we only have about 14 or 15, somewhere between 15 and 20 students taking this thermal physics course. And that is not unusual for students at other large state universities. There's about 30,000 students at this university altogether. In this class, about 90% of the students were physics majors or physics engineering double majors. And 90% were upperclassmen, juniors or seniors, so their third or fourth year of study. All of them had studied thermodynamics before. And the data I will talk about come from classes that I taught using a combination of lecture methods and interactive engagement methods, active learning methods. I would have used more interactive engagement methods, but part of the problem is that we don't have the materials ready. We don't have materials to give to the students to use in this active learning guided inquiry way. Part of this project is, in fact, to develop those types of materials. So I'm going to show you some of the data which come from administering sets of questions to the introductory students at the end of their instruction, more or less the last week of the class of a 15-week course. And as I said, 650 students gave written responses, and 32 students volunteered for interviews. And then we gave these same questions to the thermal physics students, the upper level students, on their first day of class, the very beginning of the semester. And we gave we gave a few additional questions as well. Let me just mention once again that these students who volunteered to be interviewed had very high grades. This is the grade distribution for all of the introductory students, the more than 420 students in this class, and that was their grade distribution. And then the grade distribution of the 32 students who became interview subjects was higher, significantly higher. So when we're talking about the difficulties that these interview students have, you have to remember that it is almost certainly the case that the average student in the class had at least that much difficulty as well. And again, this is a question I showed yesterday. The PV diagram represents a system consisting of a fixed amount of ideal gas that undergoes 2 different processes going from state A to state B. W represents the work done by the system during the process, and Q represents the heat absorbed or transferred to the system during the process. First question was, how does the work for process 1 compare to that for process 2? And since work is just integral PDV, W1 is greater than W2, so the answer we're looking for is greater than. What we found, as I mentioned yesterday, is that about 1/4 of the students in all the classes, the introductory students and the thermal physics students, the upper level students, about 20% of them. Notice, by the way, 2003, 20%, and in 2004, also 20%. We got the same results 2 years in a row with that upper level thermal physics class. And about 30% among the introductory students said that the work would be equal in both processes. And the types of explanations were saying that the work was path independent, the same regardless of the path taken. And both the introductory students and the upper level students made arguments that they believed that the work was independent of process. That's without elaborating, without belaboring the point, that's what they thought. And the same types of explanations were given by the introductory students. Now, why they came to believe this, we don't know in detail. Well, one of the things we haven't done and we'd like to do is to find out more about the origins of these ideas that the students had. Did it come from being confused with the mechanical forces in the context of mechanical work in the context of conservative forces? That's certainly a possibility, but we don't know. We don't know if they were thinking about it directly, but it seems plausible. We then had a similar question about heat. Q for process 1, how does that compare to Q for process 2? And since the change in the internal energy is the same for both process 1 and process 2, and more work is done by the system in process 1, the Q, the heat transferred in form of heat, has to be greater in process 1. So the answer we're looking for is greater than. And once again, we found many students who claimed it was the same, and in this case, a higher percentage than previously, than when the work question, between 30 and 50%. And again, the explanations they gave made it clear that they thought that the heat transfer was the same for any processes that started and ended at the same initial and final states. The heat transfer is the same because they're starting and ending on the same isotherm. So again, the students were claiming that the heat transfer was independent of process. It was as if it were behaving as if it were a state function. Something that obviously they never heard from any instructor and never read in any textbook, but they somehow came to believe that. And this was a large proportion of the students. Now, if instead we look at the students who got the correct answer, Q1 greater than Q2, if we simply look at the students who gave the answer, now forgetting about the explanations they gave, we seem to have this paradox that the introductory students had a higher proportion of correct answers than the upper level thermal physics students. However, what we find is that it's essential to look at students' reasoning and the explanations they write to justify their answers to questions of this type. So we looked at the explanations they gave, and if we now consider students who gave the correct answer with a correct or at least a partially correct explanation, we see that the upper level students actually did better than the introductory students, 30% correct compared to only 11 or perhaps 19% correct for the interview sample. In any case, no matter how you look at it, it's not a very good performance on a question that is at least supposed to be not very difficult, considering that they have already studied the material extensively. And notice again that this is true in 2003, 30% correct, and in 2004, 30% correct. Very consistent results. One of the things we look for in this type of work, as I sort of mentioned yesterday, is consistency of results. There are big fluctuations in the types of responses you get from students. And it's very hard to believe your results when you only see it one time. And I never do. So when I was very happy that, you know, the results are bad. It's very bad to see that only 30% got it correctly. But as a researcher, I'm very happy to see that I got the same number 2 years in a row, because then I can believe that this really is something that is probably a generalizable result. More likely than not, now that I've seen it twice. And this is consistent with what other researchers have seen. And this also makes sense that the performance of the upper level students is better than that of the introductory students, although not very much better. Just an example of another question that the students responded to. This is from the Loveroot, Couch, and Heron paper. An ideal gas is contained in a cylinder with a tightly fitting piston. Several small masses are on the piston, see the diagram. Neglect friction between the piston and the cylinder walls. The cylinder is placed in an insulating jacket, and a large number of masses are added to the piston. So we're showing them adding masses to this piston. Tell whether the pressure, temperature, and volume of the gas will increase, decrease, or remain the same. Explain. And you notice this has an insulating jacket. And the results on this question are very interesting. Here's an example of a correct response from one of the thermal physics students. Work is done on the gas, but no heat transferred out, so T increases. So this question was given to the thermal physics students again on the first day of class, and they've all studied thermodynamics in their introductory course. And I will show you the percentage of correct responses we got on this question. In 2003, we got 20% correct responses, and in 2004, we got 20% correct responses. Again, a very consistent result. And this is consistent with the results on that other question that I just showed you, the PV diagram. And what it says is that the students may have studied this material in their introductory university course, but they still have difficulties with it, with the first law of thermodynamics, basically. It's interesting to look at some of the incorrect responses. The temperature will remain the same because there is no heat transfer. So they're associating temperature with heat. Temperature should stay the same due to the insulating jacket. Same difficulty. PV equals nRT. T will stay the same as a drop in V will trigger an equal rise in pressure. This is typical of the type of mistaken reasoning students apply to not just the ideal gas law, but other laws, other formulas, other equations that involve several variables. They have difficulty dealing with several variables simultaneously and variations in the variables. A related question, which we adapted from materials constructed at the University of Maine, involve an adiabatic expansion. This is a system consisting of a mole of ideal gas. This is the initial state of the system. This is supposed to indicate a insulating jacket. And there is an expansion. It says it's an adiabatic expansion, so there's no heat transfer. And we ask whether the change in internal energy is positive, negative, or zero. So it's expanding, but there's no heat transfer. So the system is losing energy by doing work on the surroundings, and the change in internal energy has to be negative. Now what we found is that the students who got, and it's a small number of students who got a correct answer on that insulated piston question that I showed a moment ago, which is only 24%. I had to make a correction because some students didn't show up for the final. So for this sample, instead of 20%, it's 24% of the students in the class. They got that adiabatic expansion problem correct. None of them got it incorrect. There's not too many of them, but anyway, they got it correct. The students who got the insulated piston problem incorrect on the pretest, at the end of the course, most of them did get the adiabatic expansion process question correct, but some of them got it wrong. And there's not enough numbers here. The numbers obviously are too small to make any kind of statistically significant conclusion, but we do wonder whether this means that the insulated piston problem is actually a more difficult problem, even though it treats essentially the identical process. But slight changes in wording, slight changes in context can make a difference in how students respond. This is something that we have to investigate in more detail. We did find a special difficulty that students had with free expansion processes. Free expansion processes are very important in the course of this instruction because they're used as examples of irreversible processes. They're used as examples when discussing entropy in the second law of thermodynamics. And here what we had is a question dealing with a free expansion into a vacuum, where again the gas is contained within an insulated container, and the initial state has half the volume of the final state. And students were asked to rank the magnitudes of the heat and the work done and the change in the internal energy and so on. They were told they were supposed to compare, what they were supposed to do is compare the isothermal expansion process here to the free expansion into a vacuum process, where the initial state, that is to say the initial volume of these two, and the initial temperature and the initial pressure were equal, and the final temperature, volume, and pressure were equal. And they were supposed to compare the magnitudes of the heat transfer and all these other quantities for the isothermal expansion and the free expansion. That's the context of this question. Now, we spent a lot of time in class discussing free expansions in terms of related to entropy's state function property. We did homework assignments, we did group work. Nonetheless, we got a relatively poor performance on that question. I won't discuss the data in any detail. I'll just say that we got less than 50% correct on that question on the final exam. There are different types of errors. They thought the temperature had to change, even though we said the initial and final states were the same as for the isothermal process. They thought the internal energy had to change, even though there's no work done and there's no heat transfer, and so on. There are a lot of different difficulties. And the difficulties that students had with the first law concepts prevented them in many cases from realizing that the temperature would not change in this ideal gas-free expansion. And if you don't realize that the temperature doesn't change in that process, then there's no way to get to the other, to go along the reasoning relating it to entropy being a state function and the entropy increasing, or actually the entropy not changing. The entropy change for the free expansion process being the same as the entropy change for the isothermal expansion process, is what I mean to say. And this is consistent with results at the University of Maine. We also gave a number of questions on cyclic processes, as I discussed yesterday. This context was a fixed quantity of ideal gas contained within a metal cylinder that's sealed with a movable, frictionless, insulating piston. Cylinder surrounded by a large container of water with high walls, and considering process 1 here. So here's the system, the ideal gas, the insulating piston, movable piston, and the water bath, water container. The system starts at room temperature. Everything's at room temperature. And once again, this diagram was not shown to the students, but this describes the process that we go from A to B, C, and D. So that's the initial state A. At the beginning of time A, the water container is heated, and the piston very slowly moves upward. At time B, the heating of the water stops, and the piston stops moving, so we go from A to B. And now we asked an initial question right away. During the process that occurs from time A to time B, which of the following is true? Positive work is done on the gas by the environment, the positive work is done by the gas on the environment, or no net work is done on or by the gas. Now, this question, the intention was to put a really simple question on there just to sort of get them started and give them confidence and so on. I didn't really anticipate that to have any difficulty with this question. And maybe I should have. Of course, it's a very basic concept of thermodynamics that if part of the system boundary is displaced in a quasi-static process, there's an energy transfer between the system and the surroundings. In the study done by Lubricats, published in the paper by Lubricats and Heron, they found that many students, most students, had difficulty using the concept of work in the context of an adiabatic compression. And so here we're looking at a slightly different context. This is an isobaric expansion, and then in a moment it'll be an isothermal compression. So, question 1. What kind of work is done? Because it's an expansion, of course, the gas system is doing work in the surroundings. Positive work is done by the gas on the environment. And most of the students gave the correct answer on this. 69% of the interview sample and 62% of the thermal physics students. However, a significant minority said that positive work is done on the gas by the environment. About 1/3 of each of those groups. Some explanations, very interesting explanations. The water transferred heat to the gas and expanded it, so work was being done to the gas to expand it. The environment did work on the gas since it made the gas expand and the piston moved up. Water was heating up, doing work on the gas, making it expand. It's interesting to look at the language here. The arguments sound plausible. They're completely wrong. And they're mistaken uses of the language, but it shows some of the confusion in which the students can get. What we find is that many students are using the term work to refer to what is really a heating process. Nearly 1/3 of the sample, nearly 1/3 of the interview students and the thermal physics students believe that the environment does positive work on the gas during the expansion. Now, that's bad enough that they are confused about what the work means, but what is worse is that they were also confused about which way the energy was transferred. And so we had additional questions that showed that half of the students, even more than that 1/3, didn't realize that energy is transferred away from the gas during this expansion process. And I'll show one of those questions. So here's the next part of this process. Beginning at time A, the water is heated and the piston slowly moves upward. At time B, the heating of the water stops and the piston stops moving. Now, empty containers are placed on top of the piston as shown. Small lead weights are gradually placed in the containers one by one, and the piston is observed to move down slowly. While this happens, the temperature of the water is nearly unchanged, and the gas temperature remains practically constant. At time C, we stop adding lead weights to the container and the piston stops moving. The piston is now at exactly the same position it was at time A. So what we've described just now is this isothermal compression from B to C. And of course what happens is that because the system is contained in this large container of water, the water acts as a thermal reservoir and undergoes essentially zero temperature change. And so this is a virtually perfect isothermal process. If you choose the water container big enough, you can make it as close to isothermal as you like. So there's no change in temperature. Now, the question we asked the students was, during the process that occurs from time B to time C, is there any net energy flow between the gas and the water? If no, explain why not, and if yes, is there a net flow of energy from gas to water or from water to gas? Well, the internal energy, this is an ideal gas system. It doesn't change temperature, and so there's no change in internal energy. But work is being done on the system, compressing the gas, and so that's transferring energy to the system. And so energy has to flow out of the system as heat transfer to the water. So that's the answer that we wanted the students to give. Yes, there's a net flow of energy from gas to water. What we found is that the percentage of students who gave the correct answer was 38% of the interview sample, the introductory students, and 30% of the thermal physics students. On the other hand, the majority of the interview sample and the majority of both of the thermal physics students said that there would be no heat transfer. There would be no energy transfer. Typical explanation. No energy flow because the temperature of the water does not change. Again, this association between temperature and heat. What we find is that students are, among other things, are being confused about the idea of a thermal reservoir, where you can have heat transfer to an entity that has essentially unchanging temperature. Now, admittedly, this is a pretty subtle concept, if you think about it. On the other hand, this is something that is, the idea of a thermal reservoir is used all the time in introductory thermal physics. When you talk about Carnot cycles and so on, you're talking about isothermal processes, and you always make the argument that you can carry out this process by putting it in contact with a thermal reservoir and so on. What we're finding is that students are very confused about this idea. So I won't go into the details of the other questions, or at least most of the other questions I won't go into, but I will summarize the data and say that we found that the upper level students had many of the same difficulties that the introductory students had. For instance, they failed to recognize that the kinetic energy of the ideal gas molecules, the total kinetic energy of a system of ideal gas molecules, will not change if the temperature is constant, no matter what you do to it. We said, you know, the volume changes and this and that, but the temperature doesn't change. And it's important that students realize that for an ideal gas, that means the total kinetic energy, the internal energy, doesn't change. But most of them did not realize that, or roughly half of them did not. As you see, is about 45% had this difficulty, both the introductory students and the advanced students. They failed to realize that the gas transfers energies to the surroundings via work during the expansion process, and that is more of the 59% of the introductory students and 45% of the thermal physics students. And there were other questions as well. But let me go on with this process. The piston is locked into place so it can't move. The weights are removed from the piston. The system is left to sit in the room for many hours. Eventually, the system cools back down to the same room temperature it had at time A, when cooling is completed as time D. So we're going down from C to D. And as I described this yesterday, so let me go through it pretty quickly. We asked them what happens to the net work done by the gas in the environment. And again, the net work in this process for the entire cyclic process is negative net work done by the system. And so less than 0 is the answer. We found that a small minority gave the correct answer, both introductory students and advanced students. Most of the students claimed that the net work done had to be 0. Not quite a majority of the thermal physics students. We asked the same type of question with heat. The heat transfer to the gas during the process greater than, less than, or equal to 0. Since it's a cyclic process, the net heat transfer has to equal the net work done. They're both negative in this case. So again, we wanted to see less than 0. And again, the results were that a small minority gave the correct answer. The majority said that the net heat transfer had to be 0. Most of the students thought that both the net heat transfer and the net work done had to be 0. Roughly 50% of the advanced students believed that both net work done, actually it was exactly 50%, believed that the net work done and net heat transfer had to be 0. And only one of all of these advanced students, this is the first day of class, admittedly, but they had all studied this, only one of them gave correct answers to both parts of that question, 1 out of 16. And I assure you that this is a pretty typical result. They got similar results to similar questions at the University of Maine. And it is not simply that the students at Iowa State were really bad students. This is a characteristic, I believe that this is a characteristic result. We don't have, it's interesting, we do not yet have data from other countries on this, and hopefully at some point we will. It'll be very interesting to make comparisons. So what are some of the strategies for dealing with this? Well, Loveroot and collaborators pointed out, and I think was an extremely important point, that is critical to help students solidify their understanding of the work concept. And in particular, to understand the idea of negative work. Sounds strange, but many of the advanced students do not realize that you can have such a thing as negative work. That seems like a paradoxical concept to them. It's something they hadn't really learned properly when studying mechanics. And it's critical to help students get an idea, an understanding of the nature of work as an energy transfer mechanism, not just in a mechanics context, but in a thermodynamics context as well. Heat, it's critical to stress the meaning of heat as an energy transfer, and to get students away from this tendency to think of heat as a quantity of energy that sits in a system as sort of being analogous to internal energy or total energy. And part of the problem is the way the word heat is used in many languages, in common language. It implies the idea of the energy contained within a system. So it is not, that creates additional difficulties. And to build up in the student's mind a clear contrast between heat process and a work process as an different energy transfer mechanisms. We also think that there's a lot of potential in making use of PV diagrams, diagrammatic methods in general. And as I mentioned yesterday in talking about using multiple representations, we think that there's a great value in having students translate from one representation to another. So looking at a physical description or diagrams of a process, a physical diagram where you see a piston of the type I just showed, and then drawing a PV diagram where they have to actually, that diagram that I said we did not show the students, we think it's very valuable to get the students to try to draw that type of diagram and draw conclusions from the diagram as well as from the physical description, and so on. And it's also important to recognize that some of these idealizations that we make use of in thermal physics very conveniently and very easily, they may be very difficult for many of the students. For instance, this idea that, well, the whole idea of an ideal gas and the idea that the temperature of an ideal, the relationship between temperature and kinetic energy of the molecules in an ideal gas. That's something that we treat as almost trivial, and yet we found that the students had a lot of difficulty with that idea. And also the meaning of a thermal reservoir. One of the ideas we are trying to implement is to get students to write their own justifications for some of these idealizations. As instructors, we like to simply give the students we justify these, we explain them, and we think that it may be necessary to get the students to express in their own words the reason for using these idealizations and what they mean. So just an example of how we try to incorporate some of these ideas in a worksheet, we adapted from the questions, we adapted the questions into a student worksheet where we guide them through a series of questions and answers. And so the idea is we first allow them to read a description of the entire process and then answer questions regarding work and heat. So they just read through the whole thing, and this time pretty quickly. The system is heated, the piston goes up, weights are added, piston goes down, temperature remains constant, piston is locked, temperature goes down, and then we ask them to consider the whole process and answer the questions about the net work done and the net heat. Here I'll focus on the net work done. So they're given an answer, and then we prompt them to go step by step, go back and answer specifically. From the process A to B, the net work done by the system, is that positive, negative, or zero? And we ask them to explain their answer to that. And then for the process B to C, again, the same question, is the work positive, negative, or zero? And C to D, same question. And then we ask them to rank the absolute values of the work done from largest to smallest and explain their reasoning. And finally, compare the results of that chain of reasoning to the answers they gave previously. So they can now find out the net work done, determine whether it's greater than or equal to zero, and find out whether that's consistent with their previous answer. So that's the type of problem solving we try to guide them into doing, to reflect critically on their thinking process. So let me say a few words on some of what we found in terms of student thinking on entropy and second law questions. Let me talk about heat engine questions first. We asked the students, now here I'm talking about the students in the upper level course, the advanced students. We saw that on the first day of class they had a lot of difficulties with the first law of thermodynamics, with heat and work, so we spent several weeks reviewing that material. In the course I taught, I spent a lot of time on reviewing the elementary topics, talking about cyclic processes in the first law and Carnot engines and efficiencies and so on. After that discussion was completed, I gave them as a pretest some questions that related to the second law of thermodynamics. I had not yet discussed the second law in that class. However, they had studied it in their earlier work in the introductory course 2 or 3 years earlier. And I'll tell you the results in advance, and then I'll show you the data, the detailed data. Most of the advanced students did recognize that you couldn't have a perfect heat engine, that it would be a violation of the second law of thermodynamics to have a 100% conversion of heat into work. So they did recognize that. However, most were initially unable to recognize that it would violate the second law if the engine had an efficiency that was too high, that if the engine had an efficiency that was greater than the efficiency of a reversible process of a Carnot cycle. After the instruction in the course, students did recognize, we were able to get them to understand that you could not, there was a limitation on the efficiency of the process. Nonetheless, we found that the students still had difficulty in recognizing that the net change in entropy as a state function had to be zero in a cyclic process. And I'm going to describe this now in more detail, the problems we ran into. So on the heat engine's pretest, here's the question. Consider a system composed of a fixed quantity of gas, not necessarily ideal, that undergoes a cyclic process in which the final state is the same as the initial state. During one particular cyclic process, there is heat transfer to or from the system at only 2 fixed temperatures, T high and T low. For the following processes, and now we're going to list several processes, state whether they're possible according to the laws of thermodynamics, justify your reasoning for each question. Now, the diagram was not given to the students. I'm just showing these diagrams to make it easier to discuss these processes. Heat transfer of 100 joules to the system at the high temperature, a heat transfer of 60 joules away from the system at the low temperature, and a network of 20 joules done by the system on its surroundings. So 100 joules in, 60 joules out is heat, and 20 joules of work. So obviously this violates the first law of thermodynamics, that there's energy being lost here. 70% of the students in the upper level class gave a correct answer to this question, recognizing that it was not possible. So it's not as high as you'd like, but at least it was a clear majority of the students got that correct. Here's a slightly different problem now. Heat transfer 100 joules to the system, 0 joules away from the system, and 100 joules work done by the system. 100 in, 0 out, and 100 joules of work done. Again, diagram not given. So this is a perfect heat engine. It violates the second law, and a majority of the students did get this correct. So that's a little bit reassuring. Next question. This is more complicated. During one particular cyclic process, there's a heat transfer to or from the system at only two fixed temperatures, T high and T low. Assume that this process is reversible. And we give them the numbers. Heat transfer of 100 joules to the system at T high, a heat transfer of 60 joules away from the system at T low, and a network of 40 joules done by the system on its surroundings. So we say that this is a reversible cycle. Now, we did not give them this information, but they can calculate that the efficiency of this cycle is 0.4 from the information about the work done compared to the heat input. So a 0.4 efficiency. That was not given to them. Now consider a set of processes in which T high and T low have exactly the same numerical values as in the example above, but these processes are not necessarily reversible. For the following process, state whether it is possible according to the laws of thermodynamics. Justify your reasoning for each question. Heat transfer of 100 joules to the system, 40 joules away from the system, and a network of 60 joules done by the system on its surroundings. Now, this satisfies the first law, I believe, right? Yes? But the efficiency is 0.6, and so this is greater than the efficiency of the given reversible cycle, so it's not possible. It's a violation of the second law, and nobody got that right. None of the advanced students got that question correct on, this is roughly in the middle of, or 1/3 of the way through the course. We had not discussed the second law, but they had studied that earlier in their career. And this is very consistent with the results reported by Cochran and Heron in a paper that I say it's in press. It's actually been published in the American Journal of Physics last year, where they gave similar questions to students and found similar results to students in the University of Washington. These students that I'm talking about were at Iowa State University. Those are roughly comparable institutions at a roughly comparable size. Washington is bigger, but it's the same type of place. Now I'll tell you about post-instruction results after, and I was the instructor here, so I did a lot of work, obviously, to try to get the students to do a better job with these questions. Post-instruction. A lot of instruction on the second law, a lot of instruction about heat engines and efficiencies, and we gave a post-test question, and here's the question. Consider the following cyclic processes which are being evaluated for possible use as heat engines. For each process, there's a heat transfer to the system at T equals 400 K, and heat transfer away from the system at T equals 100 K. There's no heat transfer at any other temperatures. For each cyclic process, answer the following questions. Is the process a reversible process, a process that is possible but irreversible, or a process that is impossible? Explain. And we actually give them the hint that they might want to consider efficiencies. Now, again, we did not give them this, but they are supposed to be able to calculate from things that they had studied that the efficiency of this, for a Carnot cycle operating between these temperatures, the efficiency would be 0.75. So the maximum possible efficiency for any cyclic process, any engine running between these temperatures, is 0.75. So we asked them to consider these, and let's just talk about cycle 2 here. The heat transfer of 300 joules at the high temperature and 60 at the low. You can calculate the efficiency through a variety of methods. These are things that they studied. We spent a lot of time, and they did a lot of work studying these relationships. And so you can find that the efficiency of this cycle would be 0.8, which is greater than the reversible cycle, so it's not possible. The process is impossible. And most of them got this correct, I'm happy to say. I'm not happy to say that only 60% got it correct, but at least it was a majority. Remember, I was the instructor, so I really did everything I possibly could to help them with this. Here's another example. 300 joules at the high temperature, 100 joules at the low temperature. Here the efficiency is 0.67. That is less than 0.75, so it's less than the efficiency of a reversible cycle, and so it is possible. But it's irreversible because if it were a reversible cycle, of course, the efficiency would be equal to that of the Carnot cycle. It would be 0.75. So this is possible but irreversible. And again, a majority got it correct with a correct explanation, but it was just a bare majority. And it did not meet my expectations as the instructor for the course. What was worse was their responses to the entropy question. At the end of the process, is the entropy of the system larger than, smaller than, or equal to its value at the beginning of the process? Well, it's a cyclic process, and entropy is a state function, so the net change in the entropy has to be 0. So it's equal to. And only a minority got that correct with a correct explanation. So this is still a problem for many of the students. Typically what they will do is they will try to calculate the entropy change by summing the Q over T's, not recognizing that you can't use that for an irreversible process. That's not a legitimate calculation. And so that is a typical difficulty the students have. And so what we find is that, again, as I said before, they recognize that initially they recognize that you can't have a perfect heat engine. Initially they don't realize there's a maximum efficiency. After instruction they do understand that, but they still have the problems dealing with the net change in entropy. And let me just spend a couple of minutes talking once again about the spontaneous process question, but I did discuss this yesterday, so I will just go through this pretty quickly. Once again, the question we asked them here, we asked it in several different versions. This is the more abstract version. For each of the following questions, consider a system undergoing a naturally occurring spontaneous process. The system can exchange energy with its surroundings. During this process, does the entropy of the system increase, decrease, or remain the same, or is this not determinable with the given information? Explain your answer. And then we asked the same question about the surroundings, increase, decrease, remain the same, and about the system plus the surroundings. And since there's no information given about how the system is defined, it's not determinable for the system or the surroundings, but the net has to increase for a real process. Now, we by the way, I won't discuss it, but we did give another version of this question which involved a concrete physical situation where you had an object in a room, and we had talked about the object could transfer energy to the air in the room, but you didn't know, and there was an energy transfer, but we didn't tell them which was hotter, the object or the air in the room. And we had to answer a very similar question. And I'll just say that the results were very similar. What we found is that the introductory students, both before and after instruction, did not do very well in this question. Only minority, about 40%, got it correct. Less than 40% correct. And the thinking was they tended to assume that entropy of a system always has to increase without thinking what is meant by the system. And ironically, they had trouble recognizing that the total entropy of system plus surroundings does have to increase. They thought that entropy would be conserved for some reason. So most students gave incorrect answers to all of those questions. The advanced students, this is their pre-test results. They did a little bit better, but not much. And this was the post-test where we did not have any special tutorials worked out. So there was some improvement, but not a whole lot. The advanced students realized that the total entropy would have to increase, and that was different from the introductory students. However, they believed that also there was a tendency to believe that the system entropy has to increase, even when they were not told how to define the system or any information about the system. And that's similar to the introductory students. So we've been working on this tutorial, Warren Christensen and I, where they have to consider a heat transfer process between two large metal cubes that are connected by a thin metal rod. And consider that the heat transfer. They have to decide whether the energy changes, which it doesn't, and whether the entropy changes, which of course it does. We guide them to realize that in this case you can use some of the Q over T's to calculate the heat transfer because you're dealing with thermal reservoirs. So it acts. So this is an accurate expression for the energy change of a thermal reservoir, Q over T in this case. And in this case, you can find that the total entropy has to increase. And also, we lead them to recognize that definitions of system and surroundings are arbitrary. And the results seem to be promising. Oh, this is an example of a dialogue. One of the things that we asked them to do is to consider a hypothetical, a fictional dialogue among students where one of the students says, well, the second law says that the entropy of the system is always increasing. Entropy always increases no matter what. The second student says, but how do you know which one is the system? Couldn't we just pick whatever we want to be the system and count everything else as the surroundings? And student says, I don't think it matters which we call the system or the surroundings, and because of that, we can't say that the system always increases. The second law states that the entropy of the system plus the surroundings will always increase. We found that now this is extremely explicit, and we found that if we did not have somebody expressing the exact correct answer, the students had a tremendous amount of difficulty coming up with that explanation on their own. But at least we hope that they would be able to recognize the correct answer when they saw it. So we have them analyze each statement and discuss among each other which one, whether it was correct or incorrect. So that's part of the tutorial. And what we found so far is that among the introductory students, this is pre-test and post-test without the tutorial, and with the tutorial we get an improvement. Among the intermediate students, these are second-year students, this is pre-instruction and post-instruction, we get a significant improvement. So it seems hopeful, but again, I want to stress these are preliminary results. So, what is the bottom line for all this? Well, first of all, there's no doubt, I think at this point, that the learning difficulties that have been observed among introductory students related to concepts in thermal physics persist for students even as they go on to advanced study in their third or fourth university years. We've seen too many results that are consistent to have any doubts about this. Using active learning methods, as I did and as being the instructor, does give some progress, but it's pretty slow. And many of the students still struggled a lot. And I'm sorry to report that despite my best efforts, many of the students still persisted in many of these difficulties, even towards the end of the course. And there are it's very hard. Of course, we have small samples here, only 15 or 20 students. It's hard to do statistics. Imagine doing a high-energy physics experiment where you only have, 50 events, which some of you probably do. It's hard to build up your statistics. So it's difficult to pin this down. There are large variations in performance among the different students. But nonetheless, I think that the basic results that the students have significant difficulties, that we need to try to improve instruction based on this type of research, and we have at least shown that this does give the hope of getting some improvements in learning, and presumably as we go on we'll be able to continue to get improvements in learning based on research into student understanding. And with that I'll stop. Thank you very much. I'd be happy to answer any questions about this work. Compressible water? Yeah. No, the water was never being compressed. Yes, the way something that that was a gas. It said water. It said water? Do you recall? Was it not this one or not this one? That says gas. So you mean the other one? Yeah, there was another question. Hold on. Right. Hang on. This is the system you're talking about, right? Okay, so I'll show back. I have to go back to the original diagram. So this inside here is the gas. This is the water. This is a closed jacket. So the gas is being compressed. This is, okay? The volume of the water is not changing. Okay. I'm sorry that yeah, I only showed this once, but the students, of course, when they're doing this problem, they have this sitting in front of them. They have the labeled diagram. And I don't think we didn't see any confusion on that question. Nobody asked about that, so I think we're okay on that. Other questions? Yeah.
I've noticed that many students, including myself, have difficulties in making distinction between microscopic level explanations of production of heat and heat capacity. Do you have noticed anything like this? What would be the key concepts?
So tell me a little bit more what you mean by
Yes.
a microscopic explanation.
Yes. For example, if I have a kettle of water in the stove and then let's say a cube of metal there, and I'm a teacher myself, and I ask the students to explain what are the heat, the temperatures of those objects if I warm them up at the same power.
Yes.
And then their explanations are mixed between the conduction. They might say, well, the the metal conducts the heat away, and that's the reason why.
So a confusion between conduction as an explanation and the change in the internal energy. Well, one of the things that was found with younger students is a big confusion. Yeah, you know where it comes from. If you touch something that's at a different, say they're all at the same temperature. One's a piece of metal, one's a piece of wood, and so on. This is a very common experiment that's done with younger students, right? They're all at the same temperature, but you touch them and they feel different because there's a different rate of, there are different heat conductivities. And so the younger children think, well, not just the younger children, but certainly the younger children think that, well, this is hot because it feels hot, this is cold because it's a very reasonable thing, right? Because it does feel hot and that does feel cold. Even though we know that they're all at the same temperature, they've been sitting in the same room and so on. So we know that, now if this is what you're talking about, that is a very well-known difficulty that has been explored in detail among younger students. There has been one study on university students published in the Journal of Chemical Education, which was very similar, and they found similar results. It's not surprising, and that is certainly a big confusion. We actually do not know, aside from that one study, we do not know how much of a role that particular thinking, that particular concept may play in students' thinking at the university level. So it's an interesting to consider whether that plays into it. I did not see that. In the interviews I did with students, that did not come up as far as I can determine. But it is possible that it plays a part in their thinking, because we certainly know that it's an important part of the thinking of younger students. And that's something that probably we need to investigate in more detail. That's actually an interesting point.
It has sometimes come to me that one possible source of confusion is that perhaps quite often the person delta t, and then they just use it in such a way that delta t is always calculated from that. I think that could be one reason for these wrong answers in this example where you have an isolated piston.
Yes, it certainly might be. That's a very good point. And when students are introduced to these ideas in the form of calorimetry, and in the lab, they very often do this lab experiment where they measure the heat, the temperature increase of some bunch of pieces of aluminum metal, and from that they just calculate the heat transfer. They use the fact that the heat transfers can be equated to the temperature change. So yes, I believe that could be a big part of it. I did not see that reflected in the students' explanations. And so...
Yes, but when they say that because heat is not transferred, that's why temperature cannot change. This might be...
It might be, yeah. We would like to investigate, as I mentioned before, we would like to do a more thorough investigation of the origins of these ideas that the students have. So for instance, that certainly is a very plausible ground for some of these ideas, as is the possible explanation that students are thinking about working with conservative forces. Perhaps that relates to their thinking. All I can say is that we want to investigate those. Those are good hypotheses. At the moment, we don't have any evidence that those actually play a role. But we suspect that they might. We'll have to look at it more.
I want to continue this because it's very nice point, because in this way it can happen that our teaching we will teach them to have these misconceptions.
Yes.
It would be very interesting, to, as you said, to investigate it more. And in a way, it's also one what we have been this kind of educational reconstruction, to reconstruct the course in a different form, which we normally we think this is the very easy way to start with calorimetry. But it might be for the learning not the best way.
We have, one of the things we have developed, and I didn't have time to show it here, we have developed a lot of materials that we hope will help students better understand the difference between heat and temperature, and not to get confused by that Q equals MC delta T. And so we have materials where they have to explicitly look at changes in internal energy and changes in temperature, but using gas systems, for instance, where, of course, with these other systems, you don't have to worry about the work is negligible, and you can make these simplifying assumptions that can get the students very confused. So a question is, how do we get this? Are we really causing a lot of this trouble by the way we're instructing them, or at least we're not? Maybe we're making it worse, or at least not making it better by that form of instruction. Yeah, we need to look at that more carefully. I agree. Yeah.
You talked a lot about heat engines there, and it was a kind of a traditional approach, it seems to me, you had in your teaching.
Yes.
So without specifying the real context for almost anything. And I think one of the major problems when it comes to heat engines for students can be related to not having anything real there. For instance, if we talk about work done, not work, which kind of work? Is it a sense of mass motion? Or it's very abstract, without anything real, any real physical situation there. And when we are studying this, I think we should take that one into account.
So many of the new textbooks discuss this topic in the context of real engines. They talk about automobile engines, they talk about jet engines, they talk about, a variety of Otto cycle, Stirling engines, and so on. And I think that as promising, what I worry about, though, is that it can get real. The problem with real systems and real engines is that they're very complicated. And the cycles are very complicated, and especially if you look at the details of the mechanism, like the engine, the design details, if you actually look at one of these things, a real one, they tend to be very complicated and very messy. And so the question is, how do you do it in a way that doesn't confuse the students even more?
Yes, it is certainly difficult. I'm not looking for engines like that, but something more physics. It's extremely difficult to have it.
There are these, there are some of these very simple engines that actually have a piston and a cylinder.
Something like that.
Yeah, and even those are pretty complicated, but at least you can see them and you can see them operate. I haven't myself used them, but some of my colleagues who teach in the schools also have shown me those, and they look interesting. And it probably would be good to develop a teaching sequence that combines what we're trying to do here, the more abstract expression, with some of these real systems.
Exactly.
And I think that would be a good thing to do. Not an easy thing, because you actually have to, divide. It's not like batteries. It's not like electricity, where you can just take some batteries and some bulbs and you connect them up, and it's easy to see. Well, this bulb is bright. This bulb is not bright. Setting up these real heat engines is a little more complicated, but we certainly need to try to do that. I agree. It would be good if we could. We'll have to try to do that. Other questions? Yeah.
But this is more like a comment. I realized that when you talk to the students, they quite often they understand what you say, and they are willing to accept that. But then they really do not feel that this is a heat engine.
Ah, yeah.
They have some kind of a mechanistic model that there's an explosion which happens.
Yeah.
And that explains.
Well, you know, anytime you bring in anytime you bring in a chemical reaction, you know, from the physics standpoint, things become so much more complicated, right? Because for instance, this issue of calorimetry, we're talking about just Q equals MC delta T and the confusion that can bring. In the chemistry class, remember, we started doing this with the chemist. Now, when you do chemistry in a calorimetry in a chemistry class, you have heat that comes from the chemical reaction, that comes from the forming of chemical bonds, so, which is so much more abstract and so much harder to think about. And so the students in the chemistry class have all this extra difficulty to think about. So anytime you're dealing with a mechanism that involves, like for instance, in a real engine where you have some gas that you're burning, it adds so much potential confusion. And I'm at least happy that in the physics class it's relatively simple, or at least it can be simple, compared to what the chemists have to do to teach their subject, which to me seems a lot more difficult. So I can understand why since the students, the way they meet these things is always in a real context where it's not just physics going on, there's something else going on as well, often involving chemistry, then it's a much more, the real situation is so much more complicated. So.
Yes, that's why it's often perhaps easier to start from things like Stirling engine.
Yeah, right, Stirling engine, right. Something that is.
The students really believe that it's a heat engine.
Yeah, something that, at least you can actually see these things, right, actually see one of them operate in front of you. So, you light it up with a little bit of alcohol, and you light the alcohol, and it actually chugs away for a while, so it's nice. Other questions? Yeah?
I just wonder when they learn the right way of thinking about the subject, if they will be professionals for some day, when they learn that if they aren't learning in their courses. Just what is the mechanism or the happening when they learn to that thing to do it right?
I'm sorry, could you say the question again?
When they aren't learning on
Yes.
the course, when does it happen that they learn that subject correctly?
Well, maybe they don't. I mean, it may not happen, right?
But that's just doesn't seem to be right if they're going to be going to work somewhere and they don't understand the thing.
They just become teachers.
In some cases, they don't really need to use these ideas in their day-to-day activity. They may or may not need to. In other cases, what happens is that they learn it on the job. If you actually do need to know something. I mean, I'm sure many of us have had that experience. You go through school, you study it in school, you study many years, and then you get out on the job where you have to do what you studied, and you realize you didn't really learn how to do it. But you learn by doing it on the job. I mean, there's many ways you can figure it out in the process of doing you have to.
We take study working and working life, so that we might take some of those ideas from there to our teaching.
You're saying we could do that?
Study working and those who work about that thing, how they learn that.
Oh, well, that would be interesting. I'm not sure how we would go about doing that. We'd have to interview engineers, I suppose. We'd have to go to engineers who are on the job, who actually need to know. That would be interesting to do. I'm trying to think, how could I do a research project involving that? I would have to go out, find some engineers who are using physics concepts in their work, and then interview them about what they knew and what they learned in school and how they learned it. And well, it's an interesting thought. I've never thought of doing that. It would be a hard project to do, though, because part of the problem is you don't always remember when you learn something. Sometimes you do, but if suppose we interview these engineers and they say, well, I figured it out and I'm not sure where I learned it, but I just picked it up along the way. So they might not be able to give a very good answer about how they actually learned it. But maybe they could, I don't know. It might be worth a try.
Good piece of PhD.
That's a hard project. I wouldn't assign that as a PhD project.
Longitudinal study.
Huh?
Longitudinal study.
Yeah, longitudinal study for 10 years, right? Perfect PhD project. Yes?
Were the students willing to give their own explanations? Were they willing to say them aloud?
Well, in many cases they had to write it. And now for the interviews, yes, they were, because we paid them. We told them that if they come, we would give them $10, 10 US dollars, which was a good attraction. So yes, they were willing to explain their reasoning to us. The students who had to write the explanations, most of them wrote something. Not everybody did, but the majority certainly wrote enough for us to get some idea of what they were thinking. And then later on, we did some interviews by, one of the things I did was in a class I was teaching, we couldn't record the interviews. At least I didn't ask. You know, you have to get permission to do a lot of these things. They review the ethics of the study. But I just made it a part of the course requirement that they had to do an oral exam with me. And I just took notes. I would ask them questions, they would answer because I was giving them a grade, and I would just, take notes about what they said. I didn't make a recording. So, but that was a little more difficult because there was under more pressure in that case. But in general, they're willing to express these things, yes. Yes?
In general, there is a huge difference between the concepts that students and teachers can master. So have you thought the fact that there might be some problems explaining, for example, the entropy, if it's explained in a way that the concepts which are used in the explanation are familiar to the one who already knows the thing, how it's done right, but it's not familiar to the students. I mean, especially when it's explained in, say, upper secondary school, not in university.
Right. Well, yeah. I mean, that is part of the whole problem in a sense is are we teaching this in a way that is taking account of what the students already know, and are we having them learn this in a way that is effective for them?
Yeah, I think it would be reasonable to ask the students what they know already. I mean, the preconceptions about them.
We try to find that out by asking them these questions at the beginning of instruction about things that they presumably have seen before. They've been exposed to in one way or the other. And we find out what they're thinking. So really the answer is we don't necessarily expect them to understand this at the beginning. And part of what we're doing is trying to figure out what is it they know and what is it they think so that we can make our instruction more effective. So when I say that the students have these difficulties, that may be a surprise. It's a surprise in the case of a third-year university student in physics who has studied this before. That's a surprise because we expect them to have learned it. But if I'm asking about the first-year university student who maybe has just seen it 1 year in secondary school, am I surprised at the results? Then the answer is, well, maybe it's not a surprise, but here we're at least trying to find out what is it that they think and what is it that they know so that we can do what you're saying, which is make sure that our instruction doesn't use words that are not meaningful to them, doesn't use ideas that are not meaningful to them. But in order to do that, we have to find out what they're thinking.
Yeah, I mean, in teacher education, they always tell us that the students have a language of their own, so we should use that language instead of our,
Well, we try to do that in different ways. So, for instance, the question we asked about entropy, in the question I showed talked about the system and the surroundings, okay? Now, I did ask about entropy because entropy was, we wanted to know what they think about the word entropy, what they think that means. So we asked them about system and surroundings. We had another question, which I didn't show, which doesn't use the word system and doesn't use the word surroundings. It just uses the words object and air and the room. And it does talk about energy. So we try to pose the question in different contexts, with different words, different forms of the same question, to see whether they really respond in the same way. If they don't respond in the same way, maybe the question that uses the technical terms that they're not familiar with, they give one answer to that. but the question that it uses their language that they are familiar with, they give a different answer, then we know that what you're saying is probably right, that we haven't matched the language to the student. But if they give the same answer in both cases, or in many cases, then we suspect that it's not a language problem. It's something that they really have this idea that they are expressing consistently in different ways, in different contexts, with different forms of expression, different forms of language.
Yeah, I think essentially that would be a good way to learn the new concepts.
Yeah, that's exactly right.
So one of the things that we do when we have them practice concepts and practice applying concepts is to give them different contexts, to give them to express the question in the form of using words in
one way, a different physical situation where we some different setup. We use sometimes using a diagram, a diagrammatic way to explain what's going on. It might be a PV diagram, it might be pictures, photographs, or a diagram of the piston and the water and so on. So different ways to express the same idea and have them move from one context to a different context to express their understanding of the concept in many different ways, to try to learn the concept more deeply. So yeah, that's an important point. Other questions?
Seems to be.
You have?
I might have still one. Concerning this question on entropy change in free expansion, because that seems to cause a trouble as well.
Yes.
So it's quite often so that when the students first see this question, they actually do not know what kind of things can absolutely no microscopic background on it.
Right. So one of the questions is whether it would make more sense to approach this microscopically first. I don't know the answer to that. I can tell you that some people, for some students it probably would. I know that Eric Mazur is writing a textbook right now, Eric Mazur at Harvard, where he does a very detailed, he introduces this concept with a lot of microscopic analysis and talking about the dependence on the internal energy and the dependence on volume and so on for an ideal gas, for instance. And it's very detailed. And so by the time the students get to this, they have seen a lot of microscopic justification. However, I can tell you that my experience is that that probably will not work for all students, because we did those microscopic arguments in the upper level course. I did them after the macroscopic discussion. My idea was to just introduce the ideas in a hopefully a more familiar context. Now, admittedly, the idea of entropy is very abstract, and the way you introduce it with Carnot cycles, this sort of artificial construction of Q over T, you're summing the Q over T around a cyclic process, it does seem kind of artificial. On the other hand, at least you're dealing with quantities that the students have some sense about, that a heat transfer and temperature. And when you do the microscopic approach, you really have to, it's a long discussion. I mean, to show the dependence, unless you're satisfied with saying, well, entropy is like disorder. So this is a more disordered system, so the entropy is higher. Well, students can sort of get that, but it's not very meaningful, right? That's not what you really want. You want them to have an idea about microstates and macrostates. And all I'd say is that for some students, I think that would be a good approach. But for many students, I think it would be too abstract and too difficult to try to approach it that way initially. Now, I can't prove that to you right now. That's my conjecture. But it's an important issue, and I think that it's being explored by people like Eric Mazur, who's trying this alternative method. And his book, by the way, is, I'm looking at the draft of the thermodynamics chapters. It looks excellent, and I strongly recommend it to you whenever it comes out. That'll be not right away, but something to look for. You had another question?
Yes, when there are not many questions anymore, seemingly.
What's your question?
Do you need any help with it?
No, I can do it quite well myself. You want to hear it?
Yes.
If you insist. Well, I have to take a deep breath for that.
It would be a good start for the buffet.
Huh?
A good start for the buffet.
Yeah.
Oi maamme Suomi synnyin maa, soi sana kultainen. Ei Laaksoa, ei Kukkulaa, ei vettä rantaa rahkampaa. Kuin kotimaata pohjoinen, makalisi sijaan. Ei Laaksoa, ei Kukkulaa, ei vettä rantaa rahkampaa. Kuin kotimaata pohjoinen, makalisi sijaan. Sun kukkoistukses kuorestaan kerrankin puhkeaa. Vie lämpimässä nousemaan sun toivos riemus loistassaan. Ja kerran laulu synnyn maa, korkeamman kaiun saa. Vie lämpimässä nousemaan sun toivos riemus loistassaan. Ja kerran laulu synnyn maa, korkeamman kaiun saa.